Hello, physics class. Hope you're doing well. This is technically Wednesday. You might recognize I'm in my same Wednesday live shirt, but I ditched the tie this afternoon to record our video for Thursday. This is Thursday's video. Hopefully you're watching it. Hopefully it will be interesting and you'll understand it. I know I got these weird things on my head, but that's okay. They're here for a purpose, right? Purpose number one is to make me look silly. Purpose number two, to give you a laugh. Purpose number three, to make us think about something that you probably already have experienced or know a little bit about if you have got some decent earphone technology. So what we're going to talk about today is the concept of wave interference. So you've probably heard the term interference before, passing interference in football where two people are going to catch the ball and the offensive guy has the right to the ball and the defensive guy has the right to try and block him from getting the ball, but can't like grab him, push him, shove him, has to wait till he catches the ball to tackle him or has to knock the ball out of his way. If in any way he breaks the rules, it's interference because the two guys are in very close proximity to each other and playing the game. So, that's kind of what we think about. Stop interfering with my, homework. You're getting in the way. Or stop interfering with X. You're getting in the way. Like we understand that term. It's a little bit different when it comes to waves, but we are going to use this term anyways. It's a really cool term, really cool concept for us. So I thought I would share a screen with you guys. Let me make sure I got the right, there we go, the right screen happening here. So you should be seeing something that says types of waves at the top. It's, again, a note page that I've been using on and off in this week. So it might seem like I'm, again, reading some things to you, but it's something for the sake of us staying on the same page. So here we go. The general idea of wave interference is the superposition of two or more waves in the same place and at the same exact time. Now that should kind of sound a little bit weird because when we stop and think about same place, same time in the concept of physics, two things can't occupy the same place at the same time. All right, I'm sitting on this chair. My mass is occupying the space on top of this chair, and nothing else can occupy the space sitting on this chair while I am here. One piece of mass cannot be in the same place as the other piece of mass. It's not possible. But here's the thing. Well, actually, before the thing, let's talk about cars. Two cars can't occupy the same space at the same time, right? There's a car here and there's a car behind it, right? This car can't occupy the same place as the other car. If it tries to, it's called an accident and someone's insurance is paying out some money, which is really annoying. I've been there. So drive safe. So we typically think two things can't occupy the same place at the same time, but with waves, it's different. Yes, waves are transferring energy and the matter is there, but the thing is the matter is a medium. It's the material that the energy wave travels through. So you can actually have two waves occupying the same place at the same time because the matter never really moves from its original location. Right? Think of an ocean wave. It goes up and down and up and down. An ocean wave does not change, right? It's the material of the ocean wave, the water. It does not actually change its position. The water just kind of goes up and down, up and down. There might actually be a little bit of oval up and down motion, but the water molecules stay in the same place. Right? The energy is what travels from point A to point B. Right? So that's why two waves can occupy the same place, the same space at the same exact time. And that's what we call interference, when two waves are in the same place at the same time. Now, there's two kinds of interference. There's constructive interference, and we're probably, pretty good with that concept logically. When you construct something, you build something. Essentially, think about constructing a house. You build the house from the ground up. Well, that's what we're going to talk about here with constructive interference. Constructive interference is what we call the reinforcement of waves. Right? That's what your book calls it. The way I like to think of it is actually the building up of waves. But technically, you can build up a wave crest, or you can actually deepen a wave trough. Right? And with the building up of crests or the deepening of troughs, what you're really doing is you're building up the amplitude. Right? Okay, which should kind of make sense. If two waves are coming to the same place at the same time, and you've got both of them exhibiting a certain amount of energy with a certain amount of amplitude, well, if they're both in the same place at the same time, it's like twice as much energy in that place at the same time. So twice as much energy in that location should be having the amplitude higher. The amount of energy should be built up there. So that's what we're dealing with here. Constructive interference is the building up of wave amplitudes. Now, this is where if we were in class, I would actually have a slinky out, and I'd be showing you the concept of constructive interference by shaking a slinky. And you could see one wave, and then you could see two waves actually interfere with each other, and you could see the slinky wave actually get bigger. Sorry that we can't do that. It's one of our limitations. But I think you guys will get it. You're smart. You've been working hard. I think you'll get it. And you can ask any questions you want on our at our help session or in our live class. So constructive interference. Now let me slide down here and give you a picture of constructive interference. Just kind of look past this destructive interference here for a second. There's a image here. The pink line that's here is actually the result of the combination of two waves, and it's the green wave and the blue wave. The dotted line, that's what we call like the midpoint. I usually call it the baseline because that's just what I grew up calling it. Now think of that dotted line as like a calm, flat ocean or a calm, flat lake. And then think of the blue line and the green line as little rolling waves on the lake or on the ocean. Well, if two waves are in the same place at the same time, the blue wave has a certain measured amplitude, call it a certain height, right? And the green wave has a certain height. Let's say that the blue wave is something like, 3/4 of a meter, and the green wave is actually a full meter. Well, constructive interference is where those two waves are in the same place at the same time, and they build up on top of each other. So the resulting wave is actually taller. It's been built up. It's been constructed, reinforced. And so you can see, right, there you go. It's a higher pink wave, right? Notice the waves start at the same point, crossing the baseline. They end, right, at the same point, crossing the baseline in all those locations, because this has been drawn nice and perfectly. But if we were to, actually put those numbers to it, the blue one was 0.75 meters, the green one was 1 meter. Technically, when you build those up, right, the amplitude of the resulting pink wave in this case would be 1.75 meters. Now, again, constructive interference can be actually the deepening of a trough as well, not just like building up above the baseline, but the deepening of the trough below. And so you've kind of got the same concept here, the baseline to the green, the baseline to the blue, and then you add both of those, build them on top of each other, kind of like we did vectors earlier this year in head to tail, add them together, just put them there, and you have a deeper trough. So you have the resulting constructed larger wave. Now, this is actually a legitimate situation, right? This has happened to me multiple times when I'm on the boat with my father-in-law. I'm going to stop sharing here just for a second so you can see the bigger talking head and my ridiculousness with my, earphones here. There's times where you're on a lake in a boat. My father-in-law has a 16-foot boat, nothing crazy, nothing spectacular, just a fun little pleasure craft where he mostly does fishing out of it. It's actually like his third boat he's ever owned. He bought a boat when my wife was born, and he kept that thing for like 28 years. So he made good on that investment. By no means a super rich guy or super, crazy about material possessions. He takes care of his stuff, but he's got a boat. And we'd be out on the lake, and you got the little rollers, and you're on the boat, and you're just kind of getting used to it. You're standing up, you're fishing. Story time with Mr. Hicks. You're out fishing, and you're just getting used to the basic rhythm of the boat. Some people, that basic rhythm of the boat makes them barf because they have weak stomachs. But for me, I would just get used to it. It doesn't bother me. Didn't get lightheaded. Didn't get sick to my stomach. And your body's used to it, and your feet are adjusting to the little bit of up and down of the waves. And then all of a sudden, you're not paying attention, and another boat went by 100 yards off, and you're thinking, oh, no big deal. But this big boat made this big wave. And so this big wave comes, and that wave might be this high, but now you're on another wave, and so you have to build them up. And all of a sudden, these two waves interact with each other, they interfere with each other, and they build up, right? And so you're like, whoa, you like kind of jumbled up higher. I've actually been like tossed around in the boat because the wake of one boat hit the general rolling waves of the lake, and it built it up. What really makes it kind of crazy is when I'm going to go back to my shared page. When they're actually, pretty similar in frequency, what happens is you get the combination of the two waves building you up, and the boat kind of rides high. And then all of a sudden, the trough. Ooh, I just spit on my computer screen. Yuck. That's why we have a spit zone in class, right? Anyways, when the wave builds up, right, the boat lurches up. But then if the troughs are right there after each other and they're together, you're going from this high down into this like deep low, and it's like you get jammed up, but then the boat drops way down out from underneath you, and it really jostles you around because you've built up one wave, and then right after it, you drop down into a trough. It's really kind of crazy. It's what makes people, fall on the boat. It's what makes them get sick. The up and down motion, get the lightheadedness, the craziness there that happens with constructive interference. Now, this is something that's really, really interesting. The same thing can happen with sound waves. You can have constructive interference of sound waves. You can have one sound wave with a certain amplitude, and you can have another sound wave interact in that same location at the same time with another amplitude. And so now you've got two sound waves with a certain amplitude in the same location. They build up on top of each other. What do you think that does to the sound that you hear? Hint, hint. Hence, I have these funky 3M ear protective devices. Right? Building up those sound waves on top of each other actually makes the sound louder. It builds up the amplitude of that sound wave when you have two waves interfering at the same exact place. So let me go to this little image here. It talks about constructive interference, and it's showing you a red arrow going one direction, propagating one direction. That just means the the red wave is moving across your screen from left to right, and the blue wave is propagating, moving from right to left. The waves don't actually have to be moving in the same direction. They can actually be moving opposite directions, right? So you could have this wave moving this way and this wave moving this way, and as they interfere with each other and overlap, if the crests hit at the same point, it builds the crests up. If the troughs hit at the same point, it builds the troughs down. And so you can have the waves propagating in the same direction or the waves propagating in opposite directions, and you'll still have the interference So now let's go up here to our definition of destructive interference. This one's cool. Right. If you have constructive interference, you can also have destructive interference. If constructive interference is the building up of wave amplitude, destructive interference will be the diminishing of waves or the cancellation of waves. This is actually pretty cool. You can cancel a wave. Now, typically, you only cancel a wave for the period of time where the two waves are interacting, right? Because once the waves have passed each other, they're no longer in the same place at the same time. So they continue to propagate to wherever they were going, but you can have destructive interference, the cancellation of waves. All right, sorry, just got a text message. Shouldn't have looked. That's why we have our cell phones often in our locker, and I'm not in my bedroom, so it's not often in my locker. You got me, Coleman. Okay, so basically what you've got is destructive interference, canceling waves, or decreasing wave amplitude, diminishing them. And so we'll go to this one here where you've got the label of destructive interference. You got the green wave going up with a crest, and you got the blue wave going down with a trough. And think of it like water waves. If you had a water crest, which has got all this water in it, and it was to hit a trough, wouldn't the empty trough just fill in with the crest full of water? It does. And it actually makes a flat line there. And so you can see a crest and a trough hitting at exactly the same point. And in this case, the resulting pink line is flat. Now, here's the thing. These are perfect examples. You may not always get a perfect height crest to match a perfect identical depth trough. So going to get rid of that screen and go to a whiteboard and give you, again, really bad drawings by Mr. Hicks. Right? I know you guys are sick of this, but it's probably not too much different than the real deal. That was bad. Just clear that. So we'll go over here and we will draw a wave. Now, the opposite of that wave would be something here, but let's go with a much shallower, let's call it shallower trough, right? And so we show our baseline there. Well, the crest is significantly higher. The trough is significantly lower. So what's going to happen is, even though this wave is going through destructive interference, the wave is not permanently canceled, all right, or perfectly canceled. It's just shrunk, right? It's diminished. It's shrunk. I hope you get that. I don't think it's too terribly hard. I hope I'm communicating this clearly. And if not, again, ask for help, ask questions, email, talk to me, ask when we have a live session. I am super glad to help you. I know none of this is perfect, none of this is ideal, but I think we are making it. We're doing well. So now let's talk about this concept. This is kind of what I was alluding to. If you have, all right, this top part of this image, you've got two waves that are identical. They're considered in phase, and it gives you a perfect constructive interference, a perfect doubling of the wave here. But then you've got another one where we're showing them 180 degrees out of phase. You might be looking at this saying, oh, sine waves, cosine waves, this is torture, leave me alone. We're not going into sine waves. But when they're out of phase, what that means is a crest and a trough are hitting each other at the same time. That's what you call destructive interference. Now, here is an interesting thing. You could actually do this if you have a pond near you or like a little creek. You could throw two rocks into a pond, and you could actually see the wave circles propagate from where you threw those rocks. And you can actually see this pattern. Oh man, what's it called? I'm going to check your book because I forgot this term. My bad. Mr. Hicks does not remember everything. Oh man. Yes, there it is. Uh, you could see this pattern. It's called a Moire pattern or something like that. Moire, a Moire pattern. And so you can see the waves interacting with each other. So what you've got here is, let me, I don't know if I can draw on this. I might be able to draw, or I might just be wasting time. Nope, I'm not able to draw. I won't waste your time. Right, but what we've got here is, if you can follow my little cursor, we've got a wave that came off of this, right? This rock S1, right? And then we've got another wave that came off of rock S2, and that would be this wave. And right here, those two waves are interacting. Let's call those wave crests, right? That's where you'd have a buildup, right? And anywhere you see these two waves, these two solid wave lines interacting, that would be constructive interference. Anywhere where you would see, like here, where my cursor is, that's a crest in the middle of these two. That would essentially be like a crest hitting a trough, and that would be destructive interference. Right, so you can see these patterns. They're really kind of cool. Now let's slip past that, and let's talk about sound waves, because you can actually have constructive or destructive interference with sound waves. This might look similar to a surround sound, drawing a surround sound model of where to set up your surround sound speakers for a TV stereo home theater system, right? What you've got is multiple speakers. You can have speakers coming at you, speakers coming from the side, speakers coming from the back, and all of those sound waves will interact with you. You've probably experienced this at the theater. I remember my friends talking about this when Jurassic Park, the very first one, came out, long before you guys were born. And they're like, we could hear dinosaurs like coming up from behind us, which was what was going on in the movie, although there were no dinosaurs behind them. It was just the concept of a dinosaur coming behind them with sound, right? So you can set up all these sound waves interacting forward, sideways, back, and you can actually get compressions to interact with compressions, and you can get sound waves to build up and increase in amplitude. I apologize for that cough. Or you can actually get, refractions to hit compressions, and you can actually get sound to diminish. Right? And that's where you actually have to find a good seat. I don't know if you guys have ever heard of the clip from The Big Bang Theory where Sheldon is finding the acoustical sweet spot. Look it up on YouTube. It's kind of funny. Sheldon goes into theater and he starts making noise, listening for the acoustical sweet spot, the best place to sit, so you get the best sound wave interaction. I am not promoting The Big Bang Theory because it's full of trash and nastiness, but you guys are, almost out on your own, and I'm sure you've heard of it, maybe even seen some of it. But it's kind of a silly thing. I'm not telling you to go watch Big Bang Theory tonight, though. Right, so you can actually have the sound waves interacting and actually have this pattern, and there will be good spots and there will be bad spots if the system is not designed properly. You can get these super loud spots, and you can get these actually low spots, and that's why I have these ridiculous headphones on my head. You've got this concept of sound waves interacting with each other and making things louder or making things not as loud. I think I'm done with that thing there, that file. So now we can just go back to the huge Mr. Hicks talking head and quick talk about these earphones, right? So one thing that I like to do, and I think you guys have probably picked up on that a little bit, I'd like to shoot. I shoot archery, but I also shoot guns. And so when you're shooting guns, you wear ear protection. I hate these ones because they make my ears really hot and sweaty. especially in the summertime. So I normally just wear earplugs that go in the ear, but really these are better to wear because they block out more sound and they actually go around your ears and cover up some of the bones around your ear. They say that's better. But what's even better is to go out and invest in a really good pair of these that actually have noise cancellation in them. My dad has a pair. My mom has a pair for when they go shooting. And so what it has is it has a little microchip and a microphone in there, and it senses the sound of the gun, and it basically makes an opposite wave noise and puts that opposite wave noise into little speakers inside there. And so instead of hearing a really loud gun noise, it, like in a fraction of a second, figures out how high the amplitude of that sound wave is and makes an opposite trough, right? Actually compression and opposite rarefaction. And it puts it into the into the ear protection at virtually the same exact time. And it turns a really loud gun noise into what just sounds like a clap. Literally a clap. I've worn my dad's ear protection. It's really kind of cool. They look just like this, but they cost way more than a pair of these. But they actually do a whole lot to protect your hearing. So that's some constructive and destructive interference. We're going to talk more about sound waves and how this works when we get into the sound chapter, and we're about to cross into that. We're going to put these two chapters together. So this is Mr. Hicks signing off. I hope you guys are having a good week. See you later. Bye.